Mm-hmm.
Okay, hi everyone. It's my pleasure for me to introduce our speaker today, Dr. Björn Rüffer. Um, he received master degree in mathematics from the University of Warwick in United Kingdom in 2004. And received his PhD in mathematics from the University of Bremen in Germany in 2007. After a sequence of postdoctoral appointments and fellowship at the University of Newcastle, University of Melbourne, and some other university in Japan and in Germany. He rejoined the University of Melbourne as a lecturer in mathematics in 2000, lecturer in mathematics in 2015, right? And in Newcastle now he is the convener of bachelor in mathematics program, and he also an associate editor for system and control letter, and also the journal Automatica is very top journal in control theory. Beyond we talk about a Lyapunov perspective to a projection algorithm. Björn, it's your move now.
Thank you, Min, for the kind introduction, and thank you, organizers, for the kind invitation to participate in this online webinar. And it's my pleasure to be here. Sorry, I will be looking down quite a bit during the presentation, not looking into the camera because I'm writing on my iPad. So that's unfortunately the nature of things. So here's a bit of an overview of my talk. And before I begin with that, I should mention that Min had some input about some of the technicalities. I think we talked about this multiple times lastly at earlier in this year at the Ansium conference. And yeah, and also that there are other attendees here that have deeply inspired this work, and it all goes back to talks by John Baldwin back in Newcastle, who sort of hooked me on the Douglas-Rachford theme. All right, so the talk today is about two algorithms, basically, that I will focus on. One is alternating projections. You have two sets, one is A, one is B. You start by with any point, you try to find a point in the intersection, you project onto one set, then you project onto the next set, and then from there you can keep projecting, and somehow magically this converges to a point in the intersection. So this is the method of alternating projections. And you find a point in the intersection, which is this set here. And then there is the Douglas-Rachford method, where you can again start anywhere. So here you reflect over the first set, which is sort of going the projection and then twice the distance. So you end up in this case in the set A, and then you project over, reflect over the set B. So you end up here, and then you go half the way from the initial point, which is this one here, to the point you obtain, and that's one iteration. So you go, oops, let me try that again. So you go about to here. So that's, if this is your starting point, then this is your next step, and from there you just continue. So and in this case, you're already in A, so the reflection over A would just be stay where you are, and then reflect over a B, and then go half the way, and you end up somewhere over here. So you approach a point in the intersection. In this picture, in general, you still have to project onto the first set, the one that you reflect over first, so in this case, the set A. And so these are algorithms that have been known for some time, and there's the main interest, I guess, is to understand the convergence and that is fairly well understood for the convex case. And today I'm actually going to talk about the convex case predominantly. And related to convergence is also this notion of Lyapunov functions, which can help if you can't really show directly that something converges in norm. So Lyapunov functions come to their own if you have some orbit of some dynamical system, say this thing here. Imagine this sort of spirals in some ellipsoidal fashion, so that if you have a norm ball that looks somewhat more round, that your trajectory might enter the norm ball and then leave it again. So the norm specifically wouldn't decrease along trajectory. So that's why you can't use the norm to show convergence directly. And hence people have invented a different method, and that's a direct method of Lyapunov. And I've prepared this little gimmick here, which I will just attach right there. And, oh, that's too far. So Lyapunov function is, you have your dynamics sitting in your state space, and you add basically a notion of energy to every point. So the point x0 would have an energy associated somewhere up here on the graph of the function. And basically what you have with this Lyapunov function, it's a positive definite function, and along this function, along trajectories, this function decreases towards its minimum, usually in applications centered at the origin at 0. If there's only one equilibrium point, then you can usually move that to the origin. And that's, so basically you somehow spiral down the level sets of this Lyapunov function. So if you think about walking in the beautiful Australian landscape, as long as maybe in the hills, as long as you always walk downhill, eventually you will reach a valley. And if there's only one deepest point in the valley, then eventually you reach that. So that's sort of the idea in a nutshell of Lyapunov functions. And there are some notions associated to Lyapunov functions or Lyapunov stability. So all these notions go back to about 100 years, a little over 100 years, by Alexander Lyapunov, a Russian mathematician. And he invented this direct method of using these Lyapunov functions. So the beauty there is that you don't actually have to solve the system, especially for differential equations. This is very tricky to solve a system of differential equations sometimes. So the direct test with the Lyapunov function is simply to check that you decrease the Lyapunov function. And that is something that you can do at every point. You just have to check whether your vector field basically points downward in the Lyapunov function, and you can check that with a inner product with a gradient of the Lyapunov function. So the stability theory that arose from that, pioneered by Lyapunov, is the one of asymptotic stability. And asymptotic stability really means two concepts. There is attraction, which is the convergence we're used to, so that something converges to a point or a set. That's attraction. The set or the point is then an attractor. And there is stability. And stability means if you start close to an attractor or invariant set, that you remain close. That's the meaning of stability. And if you think of the Lyapunov function, so if you can only go downhill, that's you certainly will not increase qualitatively the distance to the minimum minimum point of that Lyapunov function. The two notions, attraction and stability, together are termed asymptotic stability. And usually when you encounter Lyapunov functions, you usually encounter Lyapunov functions that are strict, where the decrease at every time step, or the infinitesimal time step is strict, so that the Lyapunov function at the next time step is really less than what it is right now. So you're going down strictly rather than just being non-increasing. And then you get usually asymptotic stability out of these types of Lyapunov functions. Okay, so, but I want to talk about optimization algorithms, specifically these projection-based algorithms, and following the Bauschke-Combat book of 2017, which is a really nice book, Convex Analysis in Monotone Operator Theory. So that's one of my favorites. You can't really see that here. in recent years. So much information in that book. It's incredible. And so we have a Hilbert space. It's a real Hilbert space. It has an inner product that induces a norm. The norm induces the standard strong topology. And we can look at operators from the Hilbert space into itself. And these can obviously have fixed points. We denote the fixed points by fixed t, and usually the operators may be confined to, or the domain might be not the entire space. So that's perfectly fine. And then this is the busiest slide. I apologize, but I felt it made sense to just put all of these notions onto one page. But the other slides are much better, I promise you that. So there are some notions that are of relevance. You don't have to remember them all, but it makes sense to see them all in context to each other. So the one most that everyone probably is used to is the notion of non-expansiveness. That basically is Lipschitz continuity with Lipschitz constant 1. So in particular, if an operator is non-expansive, it's also continuous. And firmly non-expansive is a stronger notion than that. And this is something that some of these algorithms, the operators associated to that satisfy. And then there is a range of other notions. The last three ones really relate to the fixed point set. So here's the fixed point set. There's the fixed point set. And basically tell you that the distance to the fixed point set is not increased, or that it's actually strictly decreased in a certain more qualified sense. And the other first three properties are more about relative distance of points to each other under the action of t. And these notions are related in the way shown down here. So in particular, firmly non-expansive implies non-expansive, and that in turn implies quasi-non-expansive, which is this one here. And also we get from 1 to 6 directly via 4. So firmly non-expansive gives you quasi-non-expansive, and it also gives you strictly quasi-non-expansive. Okay, so two notions relating to the distance of a point to the fixed point set. And yeah, one is about a strict descent, so strict quasi-non-expansive, and the other one is a weak descent. So these will reappear later, but that's those are common notions in when you look at these monotone operators in Hilbert spaces. All right, and then we can, of course, compose operators. So especially when you think of the alternating projections, we do one projection after the other, projection operators specifically. And so if you have two quasi-non-expansive operators and one of them is strictly quasi-non-expansive, then quasi-non-expansive, then the composition is also quasi-non-expansive. And the other thing is if the fixed point sets is the two fixed point sets are intersect, then the fixed point set of the composition is the fixed point set or the intersection of the individual fixed points of the operators. So that's maybe not so obvious, but very useful. And then if both operators are strictly quasi-non-expansive, then so is the composition. And I omit the composition symbol. I just write this as a product, but it means composition. And non-expansiveness carries over to compositions. So if two operators are non-expansive, you compose them, you have a non-expansive operator, but that's not true generally for firm non-expansiveness. That doesn't carry over to compositions. But what you can do is if you have one operator that's non-expansive and you average it with the identity, then you get something that's actually firmly non-expansive. So that's a stronger non-expansiveness notion again. And the fixed point set is usually closed and convex if your operator is defined on a domain that's non-empty, closed, and convex. So for example, the entire space. Okay, then we can talk about projectors. I've drawn a few here for you. So projectors onto convex sets. I'm concerned with convex sets here. And projection obviously is picking for a given point x, you want to pick the point in C that is the closest to x, and that makes most sense if your set C is closed, so that, there actually is a closest point, and convex means the point is also unique, and you then get this mapping, this projector that maps the entire Hilbert space to this map C, and this map is continuous, and yeah, so that's that minimizes this distance. And it's also firmly non-expansive, and obviously the fixed point set of the projection operator for a given set C is the set C. And what you can then do, if once you have a projection, you can build a reflection. So reflection means go from one point to the projection and then take the same direction vector basically and go that same distance again, and you are at the reflection. And then the last thing we need is the notion of precompactness, and that means that a set is precompact if it is contained in a compact set, or that its closure is compact basically. And then the main problem that these algorithms under consideration are concerning here is this one. You have two sets, A and B, and they are convex and closed and non-empty. And we're looking for a point in the intersection. Okay, so that's the objective. And obviously these algorithms I mentioned will tackle that. They will tackle more because the problem also encapsulates this one. Most of you would have seen this before, I think, but I thought it's still worth mentioning. If you have more than two sets, you can build the product set. So you have sets C1 to Cn, and you want to find a point in the intersection of these n sets. So you build the product of these, the Cartesian product of these sets in n copies of your Hilbert space, basically. That's your set A, and the set B is the diagonal in this h to the n, where all individual components of this vector basically are the same. And the projection onto that is very simple to compute, and the projection onto this set is basically computing the individual projections. So if you can do that, you can solve feasibility problems for the intersection of n constraint sets. Okay, so coming to the algorithms, the first one is this alternating projections. I already briefly have drawn this picture, how that works. You basically iterate the system. You first project your point onto B and then onto A, and that's your update. And you keep doing that until you converge, hopefully, and that is the method. And there is this notion of consistency. We say the feasibility problem is consistent if it has a solution. So that's a reasonable assumption that you can solve it. And if you can solve it, then the question is, does this method actually solve it? And the answer is yes. There's this result by Bregman, which says if the problem is consistent and the set's closed, non-empty, convex, then the solutions of this algorithm converge weakly to a point in the intersection. And this is from the 1960s, or yeah, I think late 1960s or so, this result. Earlier results of a similar nature go back to John von Neumann and are about intersections of closed linear subspaces, or affine spaces, I guess. And this is essentially the most general version, and it also applies directly to intersections of more than two sets. You can actually have a composition of all the involved projectors. As long as it's a finite number, you still have the same conclusion. And now, what is this weak convergence? For someone who, like me, who comes from stability theory of dynamical systems, a lot of Lyapunov theory and so on, I don't commonly work with topology or functional analysis that much, and not so much with infinite dimensional spaces. But this goes way back for me to my student times. But so basically, strong convergence is the usual convergence. If you have a point x and a sequence xn, then we say xn converges to x if the distance of the points xn to x goes to 0. That is the usual convergence. For a weak convergence, which has this harpoon-shaped symbol, we instead want that xn minus x, if you plug that into any bounded linear functional on your, so member of the dual space of your space that you're in, which in this case Hilbert space is just the pairing with some element of another element of the Hilbert space. You basically want that through the lens of every such functional, this distance approaches 0 as n goes to infinity. So you have all these different lenses, and through every lens you want this to go through 0. And if that's the case, then you call this weak convergence to x. In general, the weak convergence is coarser, but strong convergence implies weak convergence, but we can talk about all sorts of concepts like weak to strong continuity and all these things, and things get a little more hairy with that. One important insight is that if your space is finite dimensional, like anything you encode on a computer, most of the time at least, then both notions coincide. So in particular, weak convergence then is strong convergence in finite dimensions. Okay, so the other algorithm is the Douglas-Rachford method or algorithm, and in the dynamical systems notion, I guess, is this one here. To compute the next, the update from a starting point x, you apply this operator here, which is to reflect over the first set, then you reflect over the next set, and then you average with the point where you started, and that's your update, and you keep doing that. And while you do that, this is sort of the state of the system. You also have the output of the system. So there's this notion of outputs or inputs, outputs, and states. In there's this notion, so you can have a state of a system. Sometimes some people write it like this. So there's some system that has a state x, it has an output, often denoted by y, and may have an input. It doesn't have to have all these ingredients. And so in this case, the system has an output, and the output is the projection onto the set A. And the stability questions really concern the state. So in stability theory, when you talk about stability, then that's usually a property of the state and not of the output. So then if you say something about the output, that's then a consequence of the stability of the state, say. Sometimes you can reconstruct the state from the output. If you observe the output for a certain time, then you might be able to reconstruct what the state would have been, or at least have some estimate of that. So there's certain areas that are concerned with that, but here, obviously, our motives are slightly different. And for this algorithm as well, it is known that the algorithm converges if the problem is consistent, and it converges weakly, again, to a point in the fixed point set. So the state converges to a point in the fixed point set, and the output converges to a point in the intersection of A and B. And yeah, so that's all known. This result, again, I think is from the 60s or 70s and hasn't really been improved much since then. For the convex case, there isn't really much to improve there. And these problems, or these algorithms, solve more general problems. So the feasibility problem, find a point in the intersection of A and B, is a special case really of minimizing the sum of two functions if you allow the functions to be indicator functions for sets. So if f is the indicator function for A and g the indicator function for B, then, and the indicator, of course, you have to define the indicator function in the appropriate way so that the minimum is actually when you're actually in the set. So you make it 0 when you are in the set, and you make it infinity otherwise. And in this case, then the feasibility problem is a special case of this minimization problem. That's common practice to do this. Of course, it's not smooth necessarily. The functions are not smooth, but if you use more generalized derivative techniques, you can still look at derivatives of f and g. And then if you want to find a minimizer, obviously what you do is you set the derivative equal to 0, and you try to find a point where it is actually 0. So that's leading you to this problem here. Find an x so that 0 is in the sum of two fairly general operators, so they're actually set valued, especially in the case where your functions are not smooth. So alternating projections and Douglas-Rachford apply to all these scenarios. Okay, now to the Lyapunov perspective and weak convergence. So the weak convergence that has been known now for several decades by the time Lyapunov functions entered the picture, and it came via non-convex problems. So here we're talking about convex scenarios, both A and B being convex, but the non-convex case, there's some astonishing examples. Matt is a strong proponent of applications of a Douglas-Rachford to non-convex scenarios. So he has, for example, a very nice simulation of protein folding using Douglas-Rachford. So there's some very, and solving Sudokus and that sort of thing. So all very highly discrete, sometimes highly discrete and always non-convex problems. And this Douglas-Rachford method is really successful with these methods. And then in Newcastle, a colleague, Jeff Hogan, uses the same method for finding prolates for the construction of new wavelets. So this, again, this is a non-convex problem. And yeah, so that's the observation that John Borwein made at some stage together with Bradley Sims was to that this algorithm just performs great as a heuristic also in non-convex scenarios, doesn't always converge, but often. And then the question was, how should that be proved? And they tried for a bit, and then they started popularizing this example that they came up with, which was to look at a set, which is a circle. Hang on, I can, sorry, do better than that. This is going to be a circle. There's a circle, but it's a circle without the interior. So I have to take away the interior. Sorry. Fill, no fill. There we go. And so the one set, let's say the set A is the circle, and set B is just a straight line. And so that the line is convex, but the circle itself without the interior is non-convex. And still the Douglas-Rachford method would normally find the intersection points here and here. And but somehow this problem was very resistant to proof until 2015, when Benoit constructed a Lyapunov function to demonstrate the convergence and prove the convergence for this very example. And then sometime later, Matt and Min looked at the graph of the function, and a line. So the function, I think, could be something like this. And they would also be able to find or prove that the Douglas-Rachford method would find the intersection point of the graph of the function and the line using a Lyapunov function, which was inspired by the Benoit one. And essentially simultaneously, Ohad Giladi and myself, we were looking at another scenario where we had one line, that's one set, and we had a second set, which was two lines, so the union of two lines. And we were looking at the convergence behavior of Douglas-Rachford for this very simplistic case, so maybe even simpler than the Borwein-Sims case. And locally, this scenario is if you're close to one of these intersection points, then locally you have the intersection of two lines. It's a convex problem. Everything behaves as you expect, but globally, it's you have two intersection points, and the intersection points are not, well, it's even a disconnected set. And you still observe more often than not convergence, global convergence, to either of these points. And we were able to prove this by essentially combining local Lyapunov functions for either intersection problem to a global one under certain geometric conditions. So that's where all the interest in Lyapunov functions came from, to look at these non-convex problems. But up to that point, no one had really looked at the convex case and looked at convex, the convex problem and devised Lyapunov functions for that. So that's what I'm trying to address here to some extent today. And for that, we need to look at dynamical systems on Hilbert spaces. So a dynamical system on Hilbert space, you can do this much more abstract. The space, the ambient space, only needs to be a Fréchet space, so that's a space that has a notion of convergence. It doesn't even have to have a metric. And then you can talk about these abstract dynamical systems, but of course Hilbert space is much nicer, so we just specialize this for that. Also, you can define this dynamical system in a broader sense and make it time varying, I guess. So the main observation is you want a dynamical system is basically a rule how you move forward in time. And there are three axioms that need to be satisfied. There's the one that if you don't make a step forward, then you stay where you are. That's the first one. The second one is if you make n steps forward followed by k steps, or the other way around, that's the same as going n plus k steps from the beginning. So that's some sort of semi-group type property. And we want a continuity in the state component of this map. In general, if this was in continuous time, then we would also want a continuity property in time. But in state, it basically means if you have a sequence xk going to x, then you want the phi of xk at any given time also go to phi at that time of x. And associated with this, of course, is a difference equation, x plus equals tx. And that's just the one time step map. That's t, and conversely, if you have this difference equation that also induces a dynamical system just by looking at the iterates of t along one trajectory. So obviously this covers only the case where your map t is single valued, but there are notions also for multi-valued operators t. Then we don't talk about a difference equation here, then we talk about a difference inclusion, and for that there are also the Lyapunov stability frameworks. But that's not of concern today because that's related to non-convex problems, and we want to do convex. Okay, and then associated notation for dynamical systems is the notion of an orbit. So an orbit is all the points that you visit as you go forward from a starting point x, and this orbit is then obviously the points you haven't reached yet. They don't really change as you go along in your set. So if you start a little later, say one time step later, then you still reach the remaining points, and that gives you this forward invariance property. You can also build the limit set, or also called the omega limit set. There's other limit sets as well. We are concerned with the omega limit set here, which is the forward limit set, and that is basically the set of accumulation points forward in time, and there are different representations of that. So you can take the closure of your orbit, and you look at the tail end of that, and you make the tail end start later and later and later, and you look at the intersection of all these late starting points. That gives you all these accumulation points, or alternatively, you look at subsequences in your time domain, so that the respective subsequences converge to some point z, and all these sets make up your omega limit set. And then there's this observation: if the orbit is pre-compact, then your omega limit set turns out to be invariant. So it's not only, so it's normally just forward invariant, it's always forward invariant, but it's if your orbit is pre-compact, then obviously the omega limit set is also pre-compact, and it is also invariant. Okay, so yeah, skip one there. So now we come to Lyapunov functions, and you might find this notion of Lyapunov functions a little strange given the ones you may have seen before. So this is a very general notion of Lyapunov function. So the Lyapunov function is any function that is continuous and that decreases along trajectories. So for example, or actually is non-increasing along trajectories. So let me give you an example of the Lyapunov function that works for any dynamical system. Here it is, v of x is -1. So this is a constant Lyapunov function, and it is non-increasing along trajectories, and it is continuous. And you can define this on any space, and it gives you 0 information about your dynamical system. So it's not a useful Lyapunov function. But there's many different types of Lyapunov functions you could find, and the good ones tell you a lot about your dynamical system. And so let's look at some examples. We need some machinery to make a useful statement. One is that we define this set of points where the increment, this v dot, is actually equal to 0. So that's that's basically the set where we can't say anything using the Lyapunov function. So usually we like our Lyapunov functions to decrease strictly along trajectories, and that means we can say the dynamical system is somehow moving through and not staying in a particular region of the state space. And then if the v dot is just 0, then we don't know that. So that's the reason, the region where we can't say much. And in this region, there can exist a invariant set M, and we're looking at the largest such invariant set contained in E. And this set could be infinite. So you could have, so with the Lyapunov function I just showed, v of x equal -1, the entire space could be, depending on the dynamics, could be an invariant set. For example, if you just have a shift where you just move along and move along, then everything is invariant, but also everything keeps moving. So this is not about fixed points at this stage. And then we have this notion of level sets. So that's just where all the points x where the function value is the same as a given constant. Okay, with that we can formulate this very broad stability result going back to Lassalle. It's known as Lassalle's invariance principle, and it states if you have a Lyapunov function for your dynamical system 10 is this x plus equals tx, so that's one way of writing it, the difference equation, or you can look at the dynamical system phi equivalently. So we need the dynamical system, and we are looking at a specific orbit. We pick an orbit, and if the orbit is pre-compact, so contained in a compact set, and of course it also needs to be contained in our domain of the Lyapunov function, then the omega limit set of corresponding to this to the starting point x is contained in the intersection of the largest invariant set in this set E, where v dot is equal to 0, and the level set corresponding to some constant c, which always depends on the initial condition, or in general depends on the initial condition. So this may not seem to say much at this stage, but it is a very powerful result, and it's sort of the basic ingredients to things like adaptive control, where you don't want to prove that the state specifically converges to something. You may only want that some part of the state converges to something, but your dynamical system is somehow has a more complex state, and it's all coupled, of course, and you only really care about some part of the state. Then this is a useful tool to address these types of problems. And so, for example, in constructing autopilots for planes, that's has been used for decades. Okay, so coming back to the projection algorithms and seeing how well they fit this theorem. So first of all, we need a dynamical system, so the T needs to be continuous. That's a given in both of our algorithms. The projections PA and PB are firmly non-expansive. if we compose two firmly non-expansive operators here, we get something just non-expansive in general. And but it's also strictly quasi-non-expansive, and the fixed point set is going to be the intersection of A and B. So that's nice. That's for alternating projections. And then for Douglas-Rachford, we have this TAB operators that was reflect, reflect, and average, and that is firmly non-expansive because we have the reflect, reflect. Both reflections are non-expansive. Composition of non-expansive operators is non-expansive, and then the average step makes it firmly non-expansive, and then it's also strictly quasi-non-expansive as a consequence of being firmly non-expansive. And the fixed point sets, you can characterize that, and there's of course this fabulous book by Heinz Bauschke and Patrick Combet, and there's a lot about that in there, but we're not going to go into those details. But the main observation is it's usually not the intersection of A and B. Hence, you need this projection step in the Douglas-Rachford algorithm to get into A and B, the intersection. All right, and now we can use this LaSalle result and devise a Lyapunov function, and this is something I discussed with Min at some stage earlier this year, so it's partly his work, and you didn't know. We have T to be a strictly quasi-non-expansive map, say defined on the entire Hilbert space, so that applies to both our algorithms. And the fixed point set non-empty, so that is the case if we have a consistent problem. So where we actually have a chance that this turns out to give us something useful. And then we can construct this function, very complicated, the distance of x to the fixed point set, and call that v of x, and that turns out to be a Lyapunov function for the system x plus equals tx, that's system 10. And this distance is, of course, never negative, and it's 0 exactly if we are in this set here. So it's positive definite with respect to the set. That's a common terminology in my community. And in this case, we have the set E, where v of t of x minus v of x is equal to 0. That is just the fixed point set, and so is and that's also the largest invariant set in that, of course, and it's also the level set of 0. So in other words, if you have either of these algorithms and a consistent problem, then this Lyapunov function will decrease in every time step if you're not starting in the fixed point set, and will find a point in the fixed point set and converge to that. That's basically what this says, modulo some details I'm going to mention in a slide or two. And just some computation here. So what do we need to verify that this function is a Lyapunov function? We need to check that v is continuous, which it is, because t is continuous, so v is continuous as well. Then what else? And we have positive definiteness with respect to the fixed point set, so that's all fairly straightforward. The main consideration then is to look that v is decreasing outside the fixed point set. So you pick any x that is not already in the fixed point set, and you pick any point in the fixed point set, which we only need later. So we start with v of tx, which is the distance of tx to the fixed point set. That is the norm of tx to its projection onto the fixed point set. And this is, by the triangle inequality, certainly not bigger than the distance to any other point in the fixed point set. So that's where the y comes in. And so this is by the property 6, which is the strict quasi non-expansiveness. This is strictly less than x minus y, because specifically this is a fixed point. And then we can specialize this and take as y the projection of x onto the fixed point set, so which is again a in the fixed point set. And then we have v of tx is less than this expression here, but now with y equal to this guy. And that is just the distance between x and the fixed point set, so v of x. So v is a Lyapunov function, even a strict Lyapunov function for the system with respect to this fixed point set. And that establishes that our set E, where v dot is equal to 0, is just the set where v is equal to 0, and that's exactly the fixed point set. And the largest invariant set within there is obviously the set itself, because every fixed point is invariant. So that settles that. And then we can make a little corollary here. If our orbit is bounded, then we immediately know that, we immediately know that every orbit is bounded because of this global Lyapunov function. So that's a consequence. And if it happens to be confined to a finite dimensional subspace, then that makes it pre-compact. And in that case, we can apply this LaSalle result, and we get that omega of x, so the omega limit set, so the set of all accumulation points is equal to the fixed point set. I think it probably should be is contained in. I think that's seems a bit stronger as the entire set. Okay, so probably that means, let me fix that, we can. So that's probably this. Okay, probably typo. So in particular, we have convergence. So that's strong convergence, not just weak convergence. And then we can also talk about a different Lyapunov function. So this Lyapunov function that we devised here is nice, but it has one disadvantage, and the disadvantage is that you can't compute it without knowing what the fixed point set is. And in general, you use these algorithms to find fixed points. So the premise is that you don't know what the fixed point set is to begin with. So we need something that we can actually compute a priori, and that's then this. This candidate is sort of obvious, and that's, I don't know, I think might be known by different names. So maybe a residual or something. Please correct me if that's, or confirm, either way. So we can look at this candidate here, and this time we only assume that our map T is non-expansive, and this turns out to be also a Lyapunov function, and is also obviously positive definite with respect to the fixed point set. And the proof is very simple, just following non-expansiveness, just this one short step here, very basic. But the disadvantages of this function start with the fact that this E set is potentially large, so we don't really know that, so we might have a very thick set where V dot is actually 0, so the set E, just as a reminder, is the set where all x, so that v of tx minus vx is not just non-positive, but it's actually equal to 0. And this is the set where we can't really have fine-grained information. So, and that's where our minimal set eventually lives in. And so this set could potentially be very large, and that makes this function maybe less useful. So there's that's the downside of this, but that's something that we can look at along trajectories. And then one thing to comment is that Lyapunov functions, usually they're defined on some domain. These are defined globally, but within the domain, if you want to find estimates of the region of attraction for a given invariant set, or in this case, or a fixed point set, you can, especially in non-convex problems, you can then look at the sub-level sets of Lyapunov functions, and they give you estimates of these regions of attractions. So they're always contained in the region of attraction. That makes them fairly useful in analyzing nonlinear systems in general, and these algorithms in non-convex settings. Okay, so then I should also mention that there's this well-known example by Hundal, Hein Hundal, from 2004. and his counterexample is basically for the method of alternating projections, and it is for two sets where you alternate with the projections. Obviously, you want to find a point in the intersection, and there is a single point in the intersection, that's point 0. And the method of alternating projections converges to this 0, but does so only weakly and not strongly. So that's the main benefit of that example. The main ingredient here is that you have this function p of t, which takes any real argument, non-negative real argument, and produces a vector. So the sum here together is a unit vector plus some very small vector E1. So E1 is a orthonormal basis. So basically you have something that looks more or less like a unit vector for every choice of t. And as you increase t, you basically go along the entire sequence of unit vectors, orthonormal basis vectors there. And there's infinitely many of them. And so the sequence and the example is set up in a way that you basically walk along with the projections along this this function forward with increasing t, and so that you end up with that you visit infinitely many different of these orthonormal vectors essentially, and hence your sequence cannot converge strongly to 0, but it converges weakly to 0. So that's Hundal's example, and then the question is, how is that? Where does the Lyapunov theory break down with these weakly convergent sequences? And the observation is this one: if you have a sequence that's weakly convergent but not strongly, then obviously it cannot be pretty compact. That's a pretty standard result, but it's also very easy to prove. So I'll put a proof here on the slide. But that might be something you have seen in functional analysis or so before, so I'm not dwelling on that. And I will conclude by saying that, at least for me, there always seemed to be a bit of a discrepancy between the weak convergence results guaranteeing the weak convergence for alternating projections and for Douglas-Rachford and some other algorithms that are sort of similar nature. And then the use of Lyapunov functions, on the other hand, that always seem to guarantee strong convergence. And this talk basically was my opportunity to look at this in detail and see how much, or where actually where the problem actually sits, and when you can use Lyapunov functions and when you can't, and which I think also indicates avenues to where you can extend Lyapunov theory. So, but the main takeaway is you can use these Lyapunov functions always in finite dimensional settings, and then they work really nicely. And with that, I'll just show you my reference slide. So I mentioned the book of Bauschke and Combet multiple times. There's the reference to the Hundal example, which is also very nice. And then there's this book by LaSalle, which defines these abstract dynamical systems and this very broad Lyapunov notion of Lyapunov functions. And that's the end of my talk.
Thank you, Björn, for the nice talks. So now is the time for question or comment. If you have any question or comment, please unmute and ask your question, or you can write it on the chat, please.
Björn, thanks for your talk. I have one question. So it seems like most of the results that you mentioned, as far as I can think, you need the sets to be convex in order for the operator T to be non-expansive or quasi-non-expansive or whatever. Mm-hmm. I'm wondering if you know of any cases where you could apply something like this where the sets are non-convex. So maybe I'm thinking like, maybe is there a situation where you could say prove stability for some class of sets for alternating projections, but maybe not what attractivity, or what, so, you know, you broke it up into asymptotic stability into the two parts. Would it be possible to just say, I want to know when it's stable, say?
Yeah, so usually Lyapunov functions give you stability, and if you're lucky, they also give you attractivity. So you normally don't just get one of the two, or sorry, you usually don't just get attractivity out of a Lyapunov function. Yes, everything I said applied to the case when the projections are onto convex sets, and that's maybe I didn't stress that enough. Probably didn't. So I'm guilty of preparing this very last minute, so there might be lots of typos and oversights in this presentation. Yeah, so all the non-expansiveness theory, all these nice results, and this book is full of them. All that only really applies to the case when the operators are sufficiently nice. Yeah. For the case that the sets are non-convex, or the operators more general, I think one pathway is to somehow try local arguments. So there's the dynamical system stability theory literature likes to take Lyapunov functions for or take a complicated problem and somehow break it down into smaller parts. I guess as mathematicians, we all do that all the time. But so the main theme there would be to identify a subproblem where you know a Lyapunov function, and then see that as part of a bigger picture, and from there somehow extend the Lyapunov function, or try to glue it together somehow with Lyapunov functions for other parts of the problem. So, for example, I think there's some results for convergence in the case where the sets A and B are unions of convex sets. So that's a natural candidate to be tackled with this approach, I think. But then at this point, probably using embedding that in finite dimensions if we wanted to use Lyapunov functions. Or somehow assuming pre-compactness to just rule out examples like the one by Hundal.
Okay. Okay. Any other question or comment?
Yeah, maybe one question. What is the significance of the infinite dimensional case? Because, I mean, usually we don't do any computations in infinite dimensional spaces, and usually we have some Galerkian technique or something of that kind before we do computations. So, and all the books I know are full of the Hilbert space case, and I always wonder when I see that, is that actually relevant?
I think I'm the wrong person to ask that question, but I'm very equally interested in the answer, and I think we have a few experts here who might be able to say more on it. So my background is not really a convex analysis or Hilbert space theory. It's systems and control theory. So I'm all about Lyapunov functions, but less so about convex analysis. But I think one of the uses is when you really try to do things in function spaces and which are naturally infinite dimensional. That's my guess. And of course, you can use these methods to solve systems of differential equations. That's where some of these methods originate, and that's maybe mainly of interest from a theoretical perspective. As soon as you want to compute something, of course, yes, I would say any representation is
Picard iteration or something is probably the.
Huh?
Probably Picard iteration is what you have in mind, huh?
Yes, yeah, that's.
Yeah, okay. Yeah, maybe.
Okay. I see one question on the chat from Hung. Hung, can you unmute and ask the question directly to Björn, or you want me to ask the question? Oh, okay, maybe I just.
I can try to rephrase the question as I read it. So the question is about building a Lyapunov function around this operator T. That's what the talk is about. And there are already algorithms for splitting and projection by P.
Patrick
Oh, so sorry, by Patrick Combat, yeah, which also have weak and strong convergence. So is this method better than these algorithms? So my presentation wasn't really about better or worse algorithms. It's more about a perspective to look at the algorithms using instead of classical convergence proofs common in this area of mathematics, to use something that's more of a common tool in a different area, namely these Lyapunov functions. And the Lyapunov functions have this shortcoming that the theory, at least as it's developed at this stage, doesn't really capture cases like weak convergence. And
yeah.
so it's all about strong convergence. And
Yeah,
so
that analyze the algorithm than
yeah. So the algorithms are so the method with the Lyapunov functions is somewhat algorithm agnostic, as long as you have, let's say, this strict quasi non-expansiveness, then it doesn't really matter what exactly your algorithm is. Then you can use this one Lyapunov function, or non-expansiveness. You can always use the norm of x minus tx as a Lyapunov function. So that's not about the specific algorithm.
Yes, yes. Okay. Okay, thank you. So if you don't have any here.
Oh, there's a follow-up question. So what about the case that the operator t is discontinuous? That's not covered in what I've discussed here. So discontinuity is excluded by non-expansiveness. Non-expansiveness is basically Lipschitz continuity, and that implies continuity. So the framework in the LaSalle book is about continuous operators. It only works for continuous operators, but there are results. There's some results around 2003 or 4 by Thiel and Kellett about difference inclusions, and that includes multi-valued operators, and that can include some level of discontinuity.
Okay.
I'm happy to send you a reference. If you want to send me an email, I'm happy to send you the papers.
Okay, thank you, and thank you, Björn, for the very nice talk, and thank you for the interesting discussion. So we end the seminar today now, and thank you for joining us, and see you next week.
Thank you. Thank you, everyone. Thank you.
Thank you, Björn. Thank you very much. Bye-bye.
Thanks, Regina.